Hello everyone and welcome to this new CATIA Design User Talk. In this inspiring format, our CATIA expert will discuss the special features of our software in detail to help you innovate in your daily job and take your designs to the next level. Today we're thrilled to explore the journey behind Le PINACLE, an unlimited racing car concept designed to outperform Formula One and break lap time records. So whether you're a designer, an engineer, or just passionate about innovation, this session is for you. For this, I have the pleasure to welcome on stage two guests, Sébastien Lamour, our design engineer and founder at Lamour Technologies, and Felix Rockel, our CATIA Design Industry Process Expert Manager. Hello, everyone.
Hello, Megna. Hello, Felix.
Hello, hi, Sébastien.
It's good to see you. Thank you for joining us today. As usual, could you briefly introduce yourself to those who don't know you? Perhaps first, Sébastien.
Yes. Hello to everybody. Welcome to this CATIA User Talk. I am Sébastien Lamour. I have over 20 years experience in the motorsport industry. I have been working mostly for in Formula One and for the 24 hours of Le Mans.
Thank you, Sébastien. Felix?
Yes, hello, Felix Rockel. I'm part of CATIA since 10 years. Now I'm a designer by education and I'm based in Hamburg, Germany.
Thank you, Felix. Before starting, I would like to remind our viewers that they can reach out to us during this session by asking their question in the chat, and we'll take some time at the end to answer them. Let's move on now to our CATIA Design Talk. Guys, you have the mic.
Yes. So welcome again, everybody, to have joined this talk. Today, I will present Le PINACLE racing car concept, which is a concept which I have been designed as a side and a personal project using CATIA on the 3DEXPERIENCE platform. So as I introduce myself, I am Sébastien Lamour. I am the founder and owner at Lamour Technologies, which is an engineering consultancy company dedicated to the motorsport and high-performance automotive industry. I have over 20 years of experience in this industry. I have worked in Formula One, especially for the Sauber Formula One team, and I have also worked for the 24 hours of Le Mans, for Pescarolo in particular, in a variety of engineering roles, which means I used to do mechanical design, composite, aerodynamics design, and in the recent years, I've been more a conceptual and vehicle architect designer. I am passionate about designing racing cars. For me, this is a passion which I have since my childhood, and I managed to make this passion my daily job. I am the conceptual leader and designer of Le PINACLE racing car concept, which I am using as a technical showcase for my engineering consultancy activity, which I am doing from in France. I am based just around Paris. A little bit of context on Le PINACLE. Nowadays, the technical regulations in basically pretty much all motorsport categories are very strictly regulated from a technical point of view, which limits actually the freedom and the creativity of the engineers. So for me, this project was a bit of a playground to express my out of the box thinking and creativity. And this relies on one question, which I am sure many motorsport engineers, and actually engineers from outside the motorsport industry, have probably asked themselves. What will be the perfect race car, and how it will look like if it will be entirely free of any constraints and regulations, except of course keeping the contemporary safety devices, because obviously we cannot compromise on safety. And of course, which performance numbers would it have? So this was all triggered. All the concept was triggered by those two questions. The result: this is a car that could lap up to 15 seconds faster than current Formula One machineries. If we talk numbers, this is achieved with a car which can generate up to 4.5 tons of downforce. So to put some perspective on that number, that means more than 4 times the car's own weight, which means the car could actually drive upside down on a roof. This is achieved using an engine power output of about 1,600 horsepower. And that means a car which is able to get through the corners, generating 7G of lateral forces. And again, to put things into perspective, in Formula One, we have lateral forces up to 5Gs. One of the main highlights of the concept is the use of active aerodynamics, and also the car doesn't have a front wing, which is something which I will develop a bit later. Now, what is really interesting is that the car could be built today. I mean, it is no fantasy or science fiction. I developed a concept which is using existing technology. And my estimation is that we could actually build it for less than $10 million, which is including finalizing the research and development, going through the complete car detailed design, and of course manufacturing the parts and building the car, which is less than 10% of a Formula One team's annual budget. Here you can see some renderings of the car's concept. I will go in more details a bit later during that presentation. So the secret to be able to outperform Formula One cars for 10% of the budget, it's actually quite a simple answer, because when engineers are not constrained by regulations, they often find simpler solutions which are more cost effective. So if we take the aerodynamics, for example, there is no complex front wing, there is no intricate barge boards. It's just a clean and efficient aerodynamic design working as one system. So the entire car works like a massive upside-down airplane wing, generating downforce from nose to tail. And it works with two modes. At low speeds, it uses a fan, like a vacuum cleaner, to suck the car to the track and generate more grip on the tires. And above 150 km per hour, the car will transform, panels retract, and it will switch from fan mode to pure ground effect aerodynamics. The same for the cooling. I really wanted to push all the boundaries in racing car design. So I am using 3 separated inlets for the cooling. 2 of them can close completely at high speed in order to reduce drag. I am using some technologies which were experimented in the past in Formula One, which are nowadays banned in F1, which are twisted cores to improve the overall car's packaging. Or twisted radiator cores is what I mean. And also all together with exposed header tanks to get a little bit of extra cooling through surface cooling. It also reduced a little bit the weight by opening some windows on the bodywork. So this is really again about pushing the design boundaries. What you can see on the picture, the extraction of the warm air from the radiators is done quite conventionally using louvers and chimneys on the side pod bodywork. So again, the idea was to achieve more, but with less, getting away from any technical regulation constraints. From idea to CAD model, it has been a long journey, more than 15 years in the making, between the first brainstorming for the concept until I could materialize the concept into CAD with CATIA. I have been inspired a lot by the past motorsport innovations. I am not only passionate about racing car design, I am actually also passionate about racing car history. And I think there is a lot to learn with past racing car design and past innovation, starting from some dinosaurs, as you can see on the pictures, which are really the prehistory of Formula One. So those two cars, one is a Bugatti tank, which has already a kind of aero-shaped bodywork, and the Voisin Laboratoire on the right, which has a car with the first monocoque chassis. So those two cars, they are from 1923 actually, so more than 100 years ago. And also the streamlined Formula One cars from the middle of the 1950s, when it was still allowed to cover the wheels in Formula One, which is a concept which I have kept and bring back for Le Pinacle. Fan technology, I think. For motorsport fans, those two cars are quite iconic. The Chaparral Can-Am car on the left, and from 1970, and the Brabham Formula One car on the right from the late 1970s, both using fan technology to create the vacuum and suction under the car. To increase downforce and tire grip. So yes, as I mentioned, I am using fan technology on Le Pinacle concept, which is going all together with other technologies which have been banned from Formula One, which is the active suspension technology. Is not allowed anymore in Formula One, but without any technical constraints, active suspension technology will definitely be a must-have when we have such high amount of aerodynamics loads. So, as I said, I started to think about this concept more than 15 years ago. So this started with some brainstorming. I made some napkin style of sketches, as you can see on the picture, and of course, along this 15 years journey, I had my daily professional duties in motorsport in various roles, and I've been building a lot of experience and knowledge from this professional involvement in the motorsport industry. So all this experience and knowledge I have built up along the years. Of course, I've been using that to feed this concept. So when I established my own company, I got the flexibility to actually materialize this concept into the CAD using CATIA 3D experience. So the first, when you start with a clean sheet of paper on a racing car design, the first work which needs to be done is actually the vehicle architecture of the car, which means defining the dimensions and the position for the main car components, starting from the driver installation, and then defining the size, the dimensions, and the positions of the wheels, the track width, the wheelbase, and also defining the installation of the powertrain. So in this example, at the back of the driver, which is the case for most single theater cars, and also the cooling system with radiators. So these are all the items you can see in red on the picture. And once I could define my vehicle architecture and packaging, then I could indeed start to design all the aerodynamic surfaces around the car. A little bit of a comparison between Le Pinacle and current Formula One cars. So I went for a car which has a shorter wheelbase, but also wider track width, which gives the car a much better aspect ratio. Considering Formula One, the aspect ratio of Formula One cars is mainly driven by the technical regulation, and how you can achieve the maximum performance within that technical regulation. So as I said, I could materialize this concept into a CAD model working with CATIA 3D experience. I've been using CATIA since I started my career in motorsport. I started with CATIA V4 more than 20 years ago, and then I've been evolving with CATIA V5, V6, and now CATIA 3D experience. So for me, it has always been my main daily tool for and my best companion for my daily work. So to design this concept, I have using mostly the CATIA generative shape design application using parametric master models for quick and easy design iterations. So I splitted the car's design into several areas and created master models for each of those areas. So for example, like the chassis, like the coolers and ducts, the side pods bodywork, the engine cover bodywork, the underfloor aerodynamics, the front wheel covers, the rear wheel covers, the front aerodynamics devices, even though they are really minimalistic, and the rear aerodynamics devices, like the rear wing. So I created, yes, master models for all those areas separately. Then the purpose, once I had those master models, was to build a complete car chassis. And I actually built two complete car chassis models. One was built to be able to do some CFD, which means computational fluid dynamics, which is basically aerodynamic simulations in order to simulate a wind tunnel. And also, I wanted to build up a detailed model of the car with the bodywork splits, with the fixings details, like where we are putting the bolts, the antennas, in order to generate high quality 3D renderings. So here you can see some screenshots of the detailed design model with all the splits, all details, all the antennas, which have been used to create the renderings. I will show you a quick video so that we can get a turnaround over the car's design. So as I explained a bit earlier, there is no front wing on that car because I was able to achieve the aerodynamic balance target without the requirement of a front wing. And this was achieved through the profile of the car's underfloor. So you can see the fan, as we discussed earlier, and the panels which are in open positions. So we have panels actually which are going to close to have a full ceiling of the car's underfloor when the car is in fun mode to have to generate suction. And you can see here the profile of the underfloor, which is a massive upside down airplane wing, basically from nose to tail. The CFD model. So to build up the CFD model, a CFD model in general requires some specific CAD preparations. For those who are familiar with CFD, you know that in order to run CFD, we need to define a volume domain around the car or any object actually, and this domain will be meshed. And in order for the mesh to be generated properly and not going through the car's body, that means all the surfaces on the car's model need to be 100% sealed or watertight, if you'd like, without any gaps and without any holes. And in this respect, CATIA is really powerful because it has really good analytical tools to check the connectivity between the surfaces and to check if there is no holes or gaps into the model, which makes it much easier to build up a robust and reliable CFD model. So once you've got your car's model watertight for CFD, then I could define a volume domain around the CFD model. So this is a volume which is going to be mesh and on which we will apply the airflow conditions to move around the car. Yeah, sorry for the interruption, but I think it will go back to normal in a couple of seconds. So yeah, sorry for the interruption. So as I said, once I could perform some CFD runs on the car, and you can see some pictures of the results on the right, with some pressure plots on the car's surface, and also some airflow streamlines. For this concept, I've also used the part design application in order to define some of the mechanical aspects of the car. So especially the active aerodynamics devices, like the underfloor movable panels, the side pods, variable inlets, and also the blades of the fan, which have a variable pitch, and also the rear wing drag reduction system, which is really similar to how it is done in Formula One. So you can see on the pictures, I've been using part design to define the actuators and the pistons, for example, for those active aerodynamics devices. I will give the hand to Felix Rockel, talking about active aerodynamic devices. Felix will present how we can go to the next step with CATIA, and how we can create animation with CATIA product perception experience, and also how we can use visual scripting to generate some cars variants.
Yeah, no. Hi, hello. Thank you, Sébastien. So as Sébastien has mentioned, we were together thinking what we can do with this beautiful model in CATIA to do the next steps. And so first I brought in his model, and the first thing I did was actually to visualize it, attach some materials and decals, as you can see here. This was done with CATIA live rendering. And then the next application that we decided to go for was visual scripting. We use CATIA visual scripting in this example that we want to present here, as we just have very small amount of time. We just did it for this rear pattern structure, and then for this arrow outlets right here. But there are many use cases on this car that we could tackle with visual scripting. I just have 10 minutes here for my part, so we needed to limit us a bit. So for those of you that have never seen visual scripting, I want to show a very quick example to introduce it, so you understand a bit how it actually works. So I am in CATIA visual scripting at the moment, and here I can create a design sequence. I can give it a name. I will call it live session. And it creates this little node in my scene tree, in my assembly. And then once I'm here, I have this access to this graph, and I can, with a double click, search for operators. And I will, for now, just do again something simple because of the timing constraints. But a little point, I need to make sure that I actually see what I'm creating. So create a point here that I can define by its position by coordinates, but I can also position it here in 3D. So I place it right here. Then from there, I can maybe create a polygon with the center and radius. I can maybe rotate it by 45 degrees. So here, always in the 3D, I instantly see what I'm doing right here on the graph. And I can use an affinity operator to stretch my polygon. I use the input point as the center. And then I think it should be the Y direction. I will stretch it, and maybe I can make it a bit slimmer right here to have like one of those bars. So how do I get from one of those bars now to this pattern structure? I can create a sequence where I can define the number of entities that I want to generate. So, I don't know, maybe 12. for now. Of course, those parameters I can also always change then later on. From this, I can create a curve evaluator. I will start with a minimum offset of 100 millimeters. And then for the maximum, I could maybe translate this point like that, move it towards the end. So I will not work so precise here in this example, just because of timing matters. And then I can now measure, for example, the distance between those 2 points. So distance, connect those two. And this gives me the distance value that I can then use as a maximum input here. And then I have this polygon, or the stretched polygon, and I can translate it as well by coordinates. And as I have 12 as input number here, I will receive 12 measurement outputs. And if I attach those 12 measurement outputs into the offset direction, I generate 12 segments. Or if I increase this number, 13, 14, 15 segments. And now with this curve evaluator here, I can define like its distribution. So starting maybe with bigger gaps and then getting smaller towards the end, or the other way around. Maybe something like that. And I can also generate from those curves here, of course, surfaces. So, for example, with an extrude, where I can define the length of the extrude and then intersect with the body. So that's basically how I generated this pattern here. Just as a very quick introduction, how the tool functions. And here if I double click here, you see the graph that I've created for this pattern. It's not that complex, but I have created some variants that we can toggle between. So in order to find maybe the pattern that we like, so we can go to the experiment tab, where I have all the parameters here distributed. So for example, I can make this a bit wider, those bars, and then it will update accordingly. But I can also, of course, play now with those parameters, but I can save some snapshots of the different parameter settings here, and then I can just toggle between those. And you know, if I created something that I like, I create a snapshot from that, and then I can toggle between those. Also with different shapes that are sort of starting big and then running out towards the rear. Maybe for this session now, we can maybe keep this one, why not? And then the very same thing I did actually for the air outlets. So let me just very quickly show you as well that one. So I have created in the very same way different parameters or a graph to generate those segments here for the air outlets. And I mean, this is perfect for concept design, but also I think for the racing domain, because you want to create and try out different variants in order to find the most beautiful shape or the fastest shape and result. And visual scripting offers you the possibility to play with the parameters, have a super stable parametric model where you can then adjust slightly, maybe run it again through the simulation. So here, for example, it's more open towards the front of the car and closing towards the rear. And here it's the opposite, We can try out so many different variants so quickly like that. So that's really a very powerful tool for such use cases, and many more that we will not have time to show here. Once we are here, we can go to the next application that we, together with Sébastien, figured out could be interesting to showcase here, and that's CATIA product perception experience. Sébastien has created a very beautiful model that has some functionalities, and this application offers us the possibility to demonstrate those capabilities directly on top of the CATIA data. So this is maybe one thing that is very important to highlight. So you see here that I have this selection that I've taken right here, but if I go back to my initial CATIA model and go back to experience, and I choose maybe this one instead. So it's updating in visual scripting. So I have now this sort of shape and section with the amount of sections right here. And if I go back to the PBX, you see that it's instantly inside here as well. So this is really on top of your CATIA data. If you modify anything, you will have it in your presentation as well. I can create lots of different variants, for example, for the viewpoint right here. So if I position my camera, I don't know, let's say right here, and I hit the plus, you know, I add another variant here and maybe another one right here. So you see that I have those as well now accessible here as thumbnails. And then I can go into, presentation mode and toggle between those different variants that I create. Also, obviously, the one that I've just created a second ago. And it creates me a nice camera transition between those different variants. And then, you know, we can play little animation. For example, we can tilt the wheels. Sébastien has a very interesting concept of, you know, tilting the whole part, so we can showcase and highlight something like that. Then also let's talk a bit more in detail about the active aero system of Sébastien. So we can go here, for example, show how those little flaps close at high speed to make the car more streamlined. Focus maybe then on this part that we have now worked on with visual scripting, as well as for the pattern here in the back. We can change the colors within visual scripting and switch to different color variants. Also for the entire car, like that maybe. And then if we go towards the rear, we can, for example, showcase how this fan is rotating to suck out the air under the car and press the car to the ground. Then he has this flap that is closing as well. You can see maybe even a bit better from this camera angle, because it's not only the rear flap but also the front flap closing and opening like that. Let me go again towards the front. Yeah, and that's basically how you can use visual product perception experience to generate very nice design presentation directly in the 3DEXPERIENCE platform on top of your CATIA model. And with that, I like to give back to Sébastien.
The on the active aerodynamics devices. Yes, now talking about the future for the PINACLE. As I said, for me, this is a personal and side project which I am using to a technical showcase for my business activities. But it is a lifetime project. I mean, I'm for sure I am a bit of a dreamer, and ultimately I would like to build the car and to actually go onto the track and to do the best lap times as possible and break records. But even so, the budget to materialize such a car will be less than a Formula One team budget, as we discussed earlier. It's still a long way. It's still a lot of money, and not that straightforward to secure that kind of amount of fundings. But yeah, I mean, as long as I will be alive, I will at least I will keep dreaming. I will keep working on that project and trying to find the right opportunities. Now, having said that, more realistically, I think in the short or middle term, I would like to at least bring the cars concept into a racing simulation, so that you can actually drive the car in the virtual world of racing games. So yeah, thank you for watching and listening. And if you want to get more details about the project, yeah, don't hesitate to go onto the project's website, which is highlighted below, www.lamourlepinacle.com, and I will be happy to answer some questions now.
Yeah, and now before that, I want to just say one more thing, that I'm really happy that from CATIA side we are able to support you, Sébastien. It's an amazing project. I love that you are a dreamer and the passion that you put into your project, and you created a beautiful car. And I'm really looking forward to what is about to come, and happy to be a bit part of it from CATIA side. Thank you.
Yes. Thank you, Felix, and I want to also thank you to give big thanks to the whole Dassault System and CATIA team.
Thanks.
Thank you very much, Sébastien and Felix, for this complete presentation. It was really insightful, and it gave us a great overview of this project. So thank you for this. I think it's time now for our Q&A session. So we really encourage you to take advantage of our expert presence. So please don't hesitate to ask your questions in the chat if you have any, and we will answer them. We have, by the way, some positive feedback and some work, Sébastien. So thank you for the comments. Perhaps the first question, how was defined the engine power number of 1,600 horsepower?
Yes. So actually, to define this engine power output, I've been doing some lap time simulation. I wanted to find what is the optimum engine power that you can actually and practically use for maximum performance, because there is a limit at some extent. Of course, you could say I want 2,000 or 3,000 horsepower on the car, but that doesn't make sense, because more horsepower means also a bigger engine. It also means that all the cooling systems, the drivetrains needs to be designed much stronger. So this translates into more weight. This translates into aerodynamics losses. So there is a practical limit and a practical optimum. And I figured out that this optimum was 1,600 horsepower, and this was achieved by doing some lap time simulations, as I said.
Thank you, Sébastien. We have another question from the audience. How did you determine the front and rear tire diameter and width to use on your car?
Yes, so actually, this is an interesting question because I have mixed the tires sizing on that concept. So, for example, at the front, I am using 18 inches rims, so similar to what Formula One has at the moment. So the idea of that was to get the front tires to be quite stiff. And to have maximum control on the front ride heights through the suspension system of the car. However, at the rear, I have kept the 13 inches rims from the old Formula One regulations, and the idea behind that is that at the rear of the car, and considering that the car is a rear wheel driven, so all the power is actually transmitted through the rear axle, and it's a lot of power, and there's a lot of torque. And I wanted to keep the tires at the rear quite soft in order to maximize the traction. So yeah, this was the philosophy behind having different tires diameters front and rear.
Thank you, Sébastien. Perhaps one last question: how drivers would be able to withstand 7G cornering?
Yes, that's a question which I have a lot of feedback on that topic. Actually, originally, when I designed this car, I wanted actually to design a car which can beat the driver. So I remember 15 years ago, I was for the people who are interested into chess, the board game, you know probably about. The competition between the IBM supercomputer and Kasparov, I think, if I remember right, when the computer was stronger in chess game compared to the master of chess, and actually it was a bit the idea to make a car which will beat the driver, in the sense that the driver will not be able to actually reach the limit of the car because of those massive Gs. So now, talking about that, there will still be ways for the driver to be able to sustain more Gs, because 7 Gs is quite close to what fighter jet pilots are having. So we could imagine using some kind of G suits. I know, for example, or not military ones who are quite heavy, but for example, there is this Red Bull Air Race World Championship, and for this competition, they are using some lighter G suits. So we could imagine using some G suit, but for sure, 7G cornering is going to be high constraints on the driver, and maybe at some stage the car will beat the driver, and the driver will just have to slow down.
Thank you, Sébastien. I think we will close today's Q&A session. Thank you once again to both of you for your time and participation. And special thanks to all of you who watched our CATIA user talk today and who has joined us. We hope that you appreciated this format and that you found it informative and engaging. To access everything you need about this talk, visit our CATIA Creative Design and Styling community that includes the replay of this talk, but also some tutorials, best practices, and above all, the possibility to ask your question to our expert directly in this community. And if you haven't joined yet our community, please simply create an account with an email address and a password and then log in. We would greatly appreciate your feedback, which will help us to improve our next talk. We look forward to seeing you again, our next CATIA user talk. Until then, have a great day. Goodbye, everyone.